Mhm. Okay, so let me just talk about what we're going to do today. Uh, so I do want to start off by just highlighting a few things from pages 5 through 8. But all of this, I think, should feel more familiar, just because we've been kind of circling derivatives, in some form or another ever since we started talking about that back in August. But I think limits is what feels like we need a fuller review, just because not many things uses limits after we got past that unit, except for L'Hopital's rule. But here, you know, uh, product rule, chain rule, quotient rule, implicit, and maybe we do a little bit of review with implicit. But so pages 5 through 8 will be your next set of homework that will be due on Wednesday. So tomorrow I'm not going to check any homework because you're going to be taking your assessments, FRQ assessment, during class. So I will maybe spend about 15-20 minutes kind of highlighting a few problems. And then the rest of the period, I want to use that time to go through what your FRQ test will look like. So pages 21 to 23 in packet 1. And I'll highlight a few problems. We may not be able to get through everything, but I'll highlight the problems that that may be more challenging that we can go over. And then you also picked up review worksheet 5, and I think this will be a good, between pages 21 to 23 as well as worksheet 5, and these are the best representation of what your FRQ test will look like tomorrow. So the keys attached. I'll probably spend tomorrow morning going over this. And then if there's additional time, I'll finish on worksheet 4. Okay. But ideally, you guys go home today and try this on your own and see where you are in terms of all the things that you're going to see tomorrow. Yeah.
Is there any limits on the quiz?
Yes, there will be. Like this, yeah, like L'Hopital's rule, yeah. Okay, any questions? Okay, you'll get to use your, make sure you bring your calculators. I'll send out a reminder this afternoon. And then, I'll give a more detailed, calendar after spring break, but these are basically your remaining grades, in the grade book. Finishing up, well, I finished grading the area volume quiz, so that will go in the gradebook today. So you'll see that in the gradebook today. But tomorrow will be your FRQ test. Again, the calendar was a little bit off in terms of naming the assessments. So this one will be a test. After spring break, it'll be a FRQ quiz over 2 topics. And then the last week of April, we'll have a multiple choice test split up into 2 days. There will both be 2 30-minute periods that we do that. And then the remaining grades will be completion grade. These are take-home packets that we'll do in class as well. So 5 grades remaining from now until end of school year. All right, any questions?
Tomorrow the test.
Tomorrow's the test. Yeah.
We have a health session.
Yes. Yeah. So tomorrow morning, 7:15. And also I'll have a health session this afternoon at 3:30, and then advice, and I can be available as well. Okay, so let's go to page 5. Okay, so product rule, you see up here, quotient rule, chain rule.
Nope.
I'm sorry,
Packet 2, page 5.
packet 2, right? Packet 2, page 5. So let's recall power rule conditions. In order for us to apply power rule, we got to make sure a couple things are in place, that our radicals are up in the numerator, or our radicals are converted to rationals. Sorry, variable are brought up to the numerator, and then we want to make sure we resolve any parentheses, that they're in fractional terms before power rule. So if you look at number 1 here, there's a combination of different things here. There's power rule going on. There's exponential rule, natural log. So what I like to do is just clean everything up. Some terms don't need to be cleaned up, but let's just go ahead and get everything on the same page in terms of up to the starting line, and then we can just take the derivative once every term is ready. So I'm just going to rewrite the terms that need to be rewritten. First 3 terms, there's no adjustments needed. But this next one here, 3 over x squared, I can rewrite that as what? How can I get this term ready for power rule? Yeah, 3x to the negative 2. And then root x to the 5th. Yeah, x to the 5 over 2. Okay, f prime. All right, 3x squared becomes e to the 2x. Let's derive there. Natural log of 4 minus x. U prime over u, right? That's the rule for natural log of u. Power rule, bring down the exponent, subtract 1 from the exponent. Same thing with x to the 5 halves. And then that 3 goes to 0, right? I can make it drop out. Okay, number 2, cube root of 5 minus 3x squared. We want to find the derivative. What rule can we use there? Okay, yeah, so let's rewrite it if it helps. Raised to the what power? 1/3. So we got the outside portion going on, the parentheses to the 1/3. We got the inside portion, so we'll take turns with each derivative. Inside derivative, 5 minus 3x squared, what does that become? Negative 6x, right? Okay, so just clean that up. Okay, number 3, find the equation of the tangent line at x equals 1. So to find the equation of the tangent line, what information do we need? Order pair and slope. Okay, so order pair, I can just take 1, plug into the original function, get the y value. To get the derivative, or to get the slope, I need to find the derivative. To get the derivative, I have to go through what? Quotient rule, right? Okay. So we can't take a shortcut. We can't just say, oh, x minus 3 is 1. This is negative 2x. You just do 1 over negative 2x. That's not the full derivative. We got to go through quotient rule. Okay. Okay, order pair first, though. That's the easy part. Say quotient rule, right? For derivative. Once we have our derivative, replace every x with 1. That'll get us down to our slope. Okay. Number 4, maybe we'll skip this for now, but can you identify what's involved here for the derivative product rule? Yeah. And then a little bit of what? Within the sine 2x. The fact that it's cosine u times u prime, that makes it a little bit of a chain rule. It's not a major one, but a little bit of chain rule there. Okay, let's skip that for now. Page 6. Another topic from August into September was implicit differentiation. This is where your equations feel a little mixed up in terms of the x's and y's are not nicely separated. You have something strange with the y's. The y's are it's not by itself. You got like y squared, you got multiple y terms, you have y's kind of mixed in with the x's. So we apply this derivative process when the equation is not a function. Basically, it's not y equals and all the x's on the right side. Or you see multiple y's in the equation, or kind of y's kind of mixed into the equation. So, so even though these are not functions, we can still find the derivative. We just have to kind of find the derivative implicitly because our equation, our y equation, is not explicitly defined. So the steps that we take is we're still going to find the derivative like we normally would. It's just that when we come to variables with y in it, we're going to find that derivative and then we're going to immediately include or multiply by dy dx. Okay. And then after that step is done, then it's just a bunch of moving things around. We're just trying to group things in a way that we can factor dy dx out, get that dy dx ultimately by itself, so we can get that derivative variable by itself. So let's try number 5. Okay. So number 5, we have x squared plus y squared equals 5 plus y. So we're just going to do power rule like we normally would. It's just we got to do something a little bit extra after we do the derivative for the y variable. Okay. All right. One term at a time. X squared becomes 2x. Y squared becomes good. So we find the derivative first, and then after that, then we just include a dy dx. 5 becomes 0. And then y becomes, yeah. I like to do this though. I like to put a, what's the derivative of y? 1 dy dx. You don't have to, but I do find that it's helpful, especially when you're factoring something out, that you're reminded that even when that dy dx gets factored out, that there's still a 1 sitting there. Sometimes it's easy to forget that, especially if there's not a placeholder reminding us. Okay, so now I'm just going to add and subtract in a way where my dy dx terms can sit together on the left side, and then the non-dy dx terms on the other side that I can factor dy dx out. And factor out. And then divide. Okay, so this is my slope formula. Just like other f primes, it's just that the your derivative that came from implicit will typically have a bit more information that it needs. So if I want to find the slope, I would need both the x and y values at that point rather than just the x value. Okay, let's end with 6, and then we can go to our FRQ review. 3x squared minus 2xy plus 5y squared equals 1. Do we see a need for implicit here? Yeah. Anytime you see y's kind of out of place, we know we got to do implicit. Something else though. What else do you see? Product rule. Yeah, that x times y. That's a reminder that we can't just do 2x and y's derivative separately. We got to go through a full product rule there. And then there's something else we got to be careful about within product rule.
The minus sign.
Yeah, we got to distribute that negative through once we apply product rule. Okay, so one term at a time here. 3x squared becomes 6x. I'll do product rule within this set of brackets here. So 2x, I'll treat 2x like my f. I'll treat y as my g. Okay, 2x becomes what? 2. G function, no changes. F, no changes. And g prime, y becomes what? And dy dx. Okay, so now we're out of product rule. We can clean that up later. Let's keep going though. 5y squared becomes ny dy dx. And then 1 goes to 0. Yeah, don't. I think a lot of times we forget that the 1 is also impacted. So it's not just the left side, both sides are impacted if the 1 goes to 0. Okay, so now we can distribute the negative through and then subtract in a way that we can get that dy dx by itself, and then we factor dy dx out. Spend a minute doing that, and we can move on to the next packet. Okay, so for packet 1, let's look at page 21. It says worksheet 4 at the top. Mm-hmm. You guys have a separate solution key packet. Just the pages are a little bit off on the packet. I think it says page 22 instead of page 21. So if you're looking on the packet, the pages I think maybe a little bit. So okay, part A. Find h of 4, find f prime of 7, find f double prime of 7. So here they tell us that the derivative of a function f is shown. This is the f prime graph. We're trying to find f of 4, so we know that it's going to be the antiderivative of this. We know it's going to be involving the area. I like to start off by doing this, just making sure that we're not looking at the wrong places, that we're only looking at the region between the graph and the x-axis. And so these are all triangles, 1/2 base times height for each of these. But anything above the x-axis will be positive. Anything below will be negative. So I'm just going to fill in a bunch of these areas here. So this is 1/2 2 times 4, which is 1/2. Which is going to be 4, but it's below the x-axis, so -4. 1/2 base times height. This whole thing, this is 4 times 4, 16 by 2 is 8. This is 8, but I'm just going to go ahead and just split this up into 4 and 4. All right, part A says find f of 4. We talked about last time how if you're given a derivative graph, sometimes an explicit definition is given to you. If that's the case, you can just plug in. But if an explicit is not given to you, then we got to go through final equals initial plus displacement, or you can just do the integral. You just do first theorem and then find the missing piece. So I don't have an explicit formula. I have to rely on initial plus displacement. So if I want to find f of 4, I need to have a anchor point, right? And the anchor point that's given to us is f of 10. And I'm going from 10 to 4 because I'm starting here and I'm trying to reach my destination. Now I want to read the graph, so I prefer the bounds being what? Yeah, from 4 to 10. I just have to adjust by doing what? Minus. So f of 10 is 5. And then from 4 to 10, I just have to count. From 4 to 10, I have 4 minus 4 minus 4. So negative 4 here. That's equal to 9. Okay, next up, find f prime of 7. F prime of 7. I mean, this is the f prime graph. So f prime of 7, I should look for the what? Order pair, right? So f prime of 7 equals what? Yeah, just the order pair there, negative 2.
How do you know to subtract 4 again? Minus 4, negative 4.
Because the region from 4 to 10 is this, sorry, this plus this plus this.
Okay.
All right, so 4 minus 4 is 0, 0 minus 4 is negative 4. And I just put negative 4 into that space.
Oh, that makes sense. Thank you.
If I want to find f double prime of 7, I will need to find the what at that point? Slope. What's the slope of this line segment? 2. Right. These are the same numbers, but we're arriving these at different ways, right? Just a coincidence, right? That the order pair, the y value, happens to be the slope. These are not necessarily always going to be the same. Okay. On what interval between negative 4 and 12 is the graph of f both increasing and concave up at the same time? So if we remind ourselves, this is the derivative graph. We can't just look at this graph and say, okay, increasing, there's my increasing. Okay, that's different, right? This is not the shape of the original graph. This is the shape of the derivative graph. So as a reminder, we can label our graph accordingly. Anything above the x-axis is positive slope of the f graph. Anything below the x-axis is the negative slope of the f graph. Anything on the x-axis is slope 0 of the f graph. So let's create two sign lines. Let's create a sign line for slope, and we'll create a sign line for concavity. Okay, what critical points can I place onto my slope sign line? X-intercepts, right? So negative 2, where else? Any more? 10. Now let's look at the location, right? If it's above, you're going to label it positive slope. If it's below, you're going to label it negative slope. So where we're going to start? Negative is below the x-axis. Positive. Positive. 6 to 10, negative. And then it's still negative. concavity sine line. Okay, if I want to do concavity, then I'm going to look at the what of the f prime graph. Peaks and valleys, right? The hills and valleys of the graph. So where are the critical points that I want to place onto my concavity sine line? Okay, 4, where else? 0, 8, and 10. Yeah. All right, so where do we look to, how do we interpret from our derivative graph whether we have concave up or concave down? Look at the what? Yeah, look at the slope. All right, so here, what do you see here? Positive slope, therefore we're going to translate that as what? Concave up. Okay, from 0 to 2, what do you see? Negative slope, so therefore get down. It's going to keep alternating, right? It's just going to keep going back and forth. Okay, so what interval is our graph going to be both increasing and concave up at the same time?
Negative 2 to 6. Yeah.
Negative 2, okay, 2 to 4, okay.
Oh, concave. 2 to 4 falls in the middle of 2 to 6.
Where else?
Negative 2 to 0.
Mm-hmm. Sorry. Increasing concave up.
That's it.
Yeah, that's it. Yeah. So we can say our function is increasing and concave up on those two intervals because f prime is positive and f prime is increasing. Or you can say f double prime is positive for that second reasoning. Okay, part C, we've practiced this more recently. What rule would you go through to find the derivative? Product and
Chain.
that chain. Okay. And then equation of tangent line, right? You plug -1 in to get the ordered pair. Once you find the derivative, plug that in to get the slope and then point slope formula. Okay, so I'm going to have you guys try that later on. Let's look at part D here. We see a messy limit problem, but what's the first thing that we do with any limit problem? Yeah, plug in 2 to see what's going on, right? If it gives us a real number, then we can stop, but we're at the stage where we have to just gather information, right? We don't know what's going on yet. So every x will replace with 2. Okay, how can I find g prime of 2? Table. G prime of 2 is -5. G of 4, I also need that as well. G of 4 is okay, so what do I get as a result? 0/0. So that gives me a green light to do what? L'Hopital's rule. Okay. We don't want to say that, oh, the limit doesn't exist. The point doesn't exist, but the limit still exists. There's a hole, but we know from past experiences that that 0/0 indicates that there's a hole in the graph, but the limit exists. So we need to just find the derivative of what we see in front of us, numerator and denominator separately. Okay. What do you think the derivative for e to the g prime will be? Good. So if we recall, the rule for e to the u is e to the u times u prime. So my u is whatever I see inside the exponent space. What happens to the 1 over e to the 5th? 0. It's a constant. Yeah. Okay. Denominator, g of 2x. What's the derivative there? And then the 4 goes to 0. Okay. So now that we have a different version of the expression, let's do what again? Yeah, plug the value in, and hopefully this will lead us to a real number. If it doesn't, if it gives us another 0/0, then we can do L'Hopital's rule again. So e to the g prime of 2. G double prime of 2, look at the table. 3. G prime of 4. 2. I'm sorry, g prime of 4 times 2, not times 4, sorry. Copied it wrong. So 3e to -5 over -4, or you can write it as -3 over 4e to the 5th. Any of these variations are fine. Okay, let me just highlight a few things here. Part E, is there a value such that g double prime is equal to 2/5? Oh, sorry, g triple prime. And we can tell that we don't have any g triple prime information here, but we do have g double prime. So if I have something that is a derivative away from what I'm looking for, what is that indication of? We're going to use what? There's a theorem here. Mean Valley theorem, yeah. Okay, because now we would prefer to use IVT, right? But the problem is that we don't have G triple prime for us to look for a value that's below 2/5 and above 2/5, right? We don't have that set of values, but we do have G double prime. And we know G triple prime is the derivative of G double prime. So if I can find that the slope of the G double prime graph is equal to 2/5, then I can guarantee that the slope of 2/5 will exist on that G double prime graph.
What is everything?
Mean Valley theorem.
Mean
Okay. So here is the application of mean valley theorem we're going to apply. What are our A and B values? Okay, we go to our table, find those values. Okay, so here's our reasoning by mean valley theorem. Since G double prime is continuous and differentiable, there exists a value C where G triple prime is equal to 2/5 on the interval from -4 to 6. Right, so tonight, I encourage you guys to work through pages 20 and 23, as well as worksheet 5. And then that'll be a good way to prepare for tomorrow's test, but I'll be available advisement after school and tomorrow morning for help session. All right, come get your phones.
What does triple prime say?
It's the third derivative.
For anything arbitrary.
No, it's just one derivative down. Or do you have your homework from pages 1 through 4 packet 2?
Let me check. I'm not sure.
Okay.
Look at the-
If not, you can show me tomorrow or show me.
Are you gonna do a team call for this afternoon's help session?
I can, yeah. Great. Okay, thank you.
There's no- I'd like half of it.
Okay, you can show me on Wednesday.
You have listeners advice today?
Yeah, advice, yeah.